I'm Zach Track, and this is Lab 5, three-body problem. What is a three-body problem? It's a complex, famous physics problem of three large celestial bodies of similar mass are in a system, and it is famously hard to predict. As you can see, these are very chaotic patterns, and there's no current analytical solution to predict the motion of these. In order to predict the motion of these, we need to iterate out many steps uh, of different locations and forces at those locations, like we do in this lab. Uh, the purpose is to study and apply universal gravity to model orbits of a three-body system, a system with near equal masses like stars. Um, the models we use is universal gravity force, equations, and position and velocity update formulas, as seen here. Here's the code. The initial conditions are the initial start velocities. I changed these throughout the lab, but this is the basic format of it. And here is the all the stars' masses and gravitational constant. The yellow here is the F net on star 2. The green is F net on star 3. The teal is F net on star 1. And then this is velocity and position updates of each star. Now, the results. We started with this base control system with these velocities as shown, and masses of right here, AE plus 27, 8 times 10 to the 27th kilograms, and we changed it in different ways. Over here, we changed it by changing the y component of velocity of star 1 by 500 meters per second. That's very small change for bodies this big and for distances this large. But as you can see, there was a very considerable difference in the motion of these stars. Blue came all the way down here and ended down here instead of up here. The teal, that is, purple ended right here, but this time they crashed into blue. Very different how it turned out. The blue arrow, this time I decreased the mass of one of the stars by 25%. And as you can see, that made a very big difference. But the big change is when you change the velocity of all three. As you can see, this is a completely different pattern. It starts off similar. As you can see, this loop is still there, but the ending is very different in all three scenarios. And we changed this scenario by changing one of the masses by a factor of 10. And as you can see, it basically eliminates that one star because it makes no difference on the other two stars. So it's just shot out of the system, and these have a regular orbit. That's why the three-body problem, all the bodies in the system have to be of similar mass. Results part 2. We started with this, smaller velocities in the last one, and this one we just changed velocity. Each change is a change of 250 meters per second. Again, very small for the sizes of these celestial bodies. But as you can see, very big changes and even bigger changes on another increase of 250 meters per second. They crashed very fast. Very big changes. What does it mean? Clearly, even the smallest changes in the system can disrupt the three-body system and either end up flinging everything apart or eventually causing one star to crash into another. These three-body systems are so delicate and can be thrown into chaos by the smallest initial condition changes. This is a famous problem that the system of three stars of similar mass is very hard to predict unless you know the initial conditions perfectly. But the real difficult part is finding an analytical solution to predicting the motions. Any other way to predict it is using computational methods like iterations. Why use these models? The universal gravity equation, because the system we are working with is very large and near Earth gravity will not work. we use a position update velocity formula separately instead of using kinematic equation, because kinematic equation cannot be used for non-constant forces. Thank you. That is all.